So here we are with Unit 6A Lesson B, Buoyancy. This is video number 3. We're focused on what's called Archimedes Principle. And we're going to start by asking ourselves a simple little question. Why do big, huge, massive, humongous ships float? For example, an aircraft carrier weighs almost 100,000 tons. Why doesn't it just sink like a stone? Well, Aristotle thought it was because of the shape of a thing, right? He figured if something had sharp edges, it would sink. If it was smooth and rounded like a ship, it would float. We want to ask Aristotle, why are there all these round rocks on the bottom of a river then, right? Like most of the teachings of Aristotle, it's pure nonsense. The guy who actually figured it out was Archimedes, and he discovered how buoyancy works. Buoyancy is basically an upward force that a fluid exerts on an object that object is immersed in. It causes things to float, or else results in an apparent loss of weight of something when it sinks to the bottom of that fluid. This upward force is a buoyant force. Here we go. So the basic reason behind the buoyant force is really pretty easy to understand. This picture here shows a cylinder that's immersed in some liquid. The pressure in this liquid increases with depth, so the pressure at the bottom of the cylinder is larger than at the top of the cylinder. Both cylinder ends have an equal area, okay, so the force up is larger than the force down. And of course, any forces from the side cancel each other out at the same depth. So what this results in is a net force in the upward direction. We call that net force the buoyant force. Now, of course, this applies to any object regardless of its shape. For example, imagine we have a container that we fill with some fluid and we isolate an imaginary parcel of that fluid as shown here. So this parcel is in static equilibrium. As a result of this, the parcel's weight force pulling it down has to be balanced by an upward force pushing up. That upward force is exerted by the surrounding fluid. That's the buoyant force. So the buoyant force matches the weight of that little parcel of fluid. Now imagine we could somehow remove that parcel of fluid and instantly replace it with an object having the exact same size and shape. Because the buoyant force is exerted by the surrounding fluid, and the surrounding fluid hasn't changed, the buoyant force on that new object is exactly the same as the buoyant force on that little parcel of fluid that we removed. So when an object or portion of an object that's immersed in a fluid, it displaces fluid that would otherwise fill that region of space. That's called displaced fluid. And this displaced fluid's volume is exactly the volume of the portion of the object that was immersed in that fluid. This leads us to conclude that the magnitude of the upward force matches the weight of that displaced fluid. This is called Archimedes Principle. A fluid exerts an upward buoyant force on an object immersed in or floating on the fluid. The object is buoyed up by a force equal to the weight of the fluid that it displaces. Mathematically then, Archimedes' principle is buoyant force is equal to the density of the fluid times the volume of fluid that's displaced times g. Now this makes total sense when we take it with the definition of Archimedes' principle, right? The object is buoyed up by a force that's equal to the weight of the fluid that it displaces. Weight, remember, is mg. And density, of course, is mass over volume. So when we solve that for mass, this here is just the mass of that fluid, right? So this is really just mg of that fluid, right? It's the weight of the fluid that's displaced by the object that's put into it, or the portion of the object that's put into it. What I mean is, we got this duck floating right here, right? Only part of the duck is under the water, but it's floating. The buoyant force is going to be equal to the weight of the fluid that's dispersed from this portion of the duck, just that volume of the duck. So let's look at this another way, right? Suppose we have a 2-ton block of steel. Steel's 9 times denser than water, so the 2 tons of steel will only displace about 2/9 or 0.22 tons of water. The buoyant force is not going to be nearly enough to float the block, so it will sink. That's this block of steel here. But now suppose we take that same 2 tons of steel and make a big box from it. This hollow box has a greater volume than the cube. When we set the cube on the water, then it displaces a larger volume of water than the cube itself did. So this displaced volume of fluid, which creates the buoyant force on it. As the box sinks deeper into the water, it displaces more and more water, which causes the buoyant force to increase. So when the buoyant force is equal to the weight of the box, it's going to stop sinking and it's going to float. Now also, Archimedes' principle applies to both gases and liquids, since those are both fluids. So an object surrounded by air is buoyed up by a force equal to the weight of the air that's displaced. But the density of the fluid that an object is in also plays a part in whether something will float or not. An object will float or sink depending on whether the fluid density is larger or smaller than the object's density. If the densities are equal, the object can be in a state of static equilibrium and just hang motionless in that fluid, which is shown in these pictures here. So an object will float on the surface if it weighs less than the fluid it displaces. It'll hang motionless if it is the same as the fluid it displaces, and it'll sink if it weighs more than the fluid it displaces. So the buoyant force is directly proportional to the density of the fluid. If the density of the fluid were to increase, the buoyant force will increase, which is why things will float in salt water more easily than fresh water. So we can use Archimedes' principle to figure out the density of an object and then figure out what that object is made of, because we can look at a density table and compare the calculated density using Archimedes' principle to determine the density of the object. For example, that's exactly what Archimedes did to come up with the principle named after him. The story is that he was a pretty famous guy in his day, and he was credited with a lot of different inventions. And there was the king of this Greek city that he lived in called King Hero. So King Hero was given a crown, and he wanted to know if that crown was real gold or was a fake gold. But he didn't want the crown to be messed with in any way. No core samples could be taken. He didn't want it broken in any way. So he gave it to Archimedes to figure out if this crown was real gold. All right, so this is the story. And he came up with what we call today non-destructive testing. So using a scale, he got the weight of that crown, and then he used that weight of the crown, he dipped it into water with a known density of the water, and he was able to measure the buoyant force on that crown. Well, he's able to collect the water that was displaced from that crown, right? And the buoyant force is equal to the weight of that displaced water. The volume of the object, incidentally, is also equal to the volume of fluid that's displaced. So, measuring that volume of water, you get a pretty good, accurate measure of the volume of the object. And since you're using water and you know the density of the water already, you can use all of this information to figure out the density of the material. Compare that with the known densities of known materials, and you'll be able to figure out that this crown was gold or not. So that's Archimedes' principle. It's really pretty straightforward. From here, we're going to look at fluid flow. We'll see you in class.